Limiting reactant, theoretical yield, actual yield, percent yield. So let's think about practical aspects of chemistry. We don't do that a lot because this is the classroom, right? But in many industrial applications, some of the ingredients that are needed for whatever process is being done are more expensive than others, right? And so you want to make sure that you're using up the expensive ingredient, and if you're wasting something, that you're wasting a less expensive ingredient. Another situation that can happen, unlike a recipe where you only put in some of the ingredients, when you're doing a chemical reaction and you have excess reactants, those are still hanging around when you've got your product. And so sometimes it can be difficult to separate the extra reactants from the product. So in that case, we might make that reactant that's hard to separate the limiting reactant, so then we don't have to worry about getting it out later. So we've been talking about moles, but when we're working in the lab or in an industrial situation, you're measuring things in masses. In the lab, we use grams. Industry, you might use kilograms or tons or something. So if we're going to try to find limiting reactants and theoretical yields from initial masses, we're going to have to add 2 steps to our calculation. And this is where we're going to get our grams to moles to moles to grams again. Grams to moles to grams. So this is the part we just looked at. And we've done this process in a previous section, but now we're going to do it with theoretical yield. So just kind of looking at an example without doing the whole thing. So here you're given 53.2 grams of sodium, 65.8 grams of chlorine. Here's the balanced chemical equation. Find the limiting reactant and the theoretical yield. Similar to the problem we just did, but now we're given grams. And so what we'll do is, again, we're going to have 2 calculations, but this time they're a little longer. We start with grams of sodium to moles of sodium, to moles of the product, sodium chloride, and then to grams of sodium chloride. This mole to mole thing we just did. Grams to moles, we've done that conversion before. Molar mass. Okay, so what we're doing here is we're just putting a bunch of pieces together. If you learned the pieces, then putting them together isn't too hard. So we're just going to calculate the mass of product from this reactant, and then we'll take this reactant, calculate the mass of product. Whichever one is smaller tells us the limiting reactant, and the smaller amount is the theoretical yield. There are other ways to do this problem. I've taught this concept many, many times, and I find that this is the most straightforward approach for most students. So if you want to do one of the other methods and you're successful in that, you go right ahead. But this is what we're going to do in class. So how would this look all worked out? Here we have the 53.2 grams of sodium. We're converting to moles of sodium chloride, to grams of sodium chloride. The key is putting the units in first and then putting the numbers in. So then you don't have to remember, am I supposed to multiply or divide? Just put the number with its unit and it all fixes itself. We end up with 135 grams of sodium chloride, or 108. This is the smaller amount of product. That's the yield. That's the most we could possibly make. And this is the reactant that gave us that smaller yield, so this is the limiting reactant. Notice that you cannot just look at the masses of the reactants and say, well, this is a smaller mass, that's going to limit. It's not. You just have to do the calculation. We mentioned actual yield, talking about pancakes. The actual yield is usually less than the theoretical yield. 2 main reasons. Small amount of product can be lost. or it may not form completely during a reaction. Not all reactions go to completion. What would that be correspond to in pancakes? Maybe you got tired of making pancakes, right? And so you had some batter left, but you just didn't bother to fry it up. Then your actual yield is less than your theoretical yield. Here's the equation for percent yield. We've used this in lab already. It's the actual yield divided by the theoretical. Oops. It's the part over the whole times 100. You know, my oldest son in kindergarten, there were 15 girls and 5 boys. Doesn't that sound like a fun kindergarten class? 5-year-old boys are very energetic. How would we figure out the percent boys in the class? You take the number of boys divided by the number of children in the class. 15 plus 5 is 20. And you multiply by 100%, and you get 75%. So 75% boys. And half of them didn't speak English. You think, ooh, gosh, that doesn't sound like a good first-year experience. It was awesome. He had a great teacher, he had a great time. Looks can be deceiving. Okay, so let's do one. Ammonia can be synthesized by this reaction. You can react hydrogen and nitrogen and make ammonia. What maximum amount of ammonia in grams can be synthesized from 25.2 grams of nitrogen and 8.42 grams of hydrogen? It doesn't use the word theoretical yield, does it? It doesn't even use the word yield. The maximum amount that can be made, that is the theoretical yield. Well, I don't really have space under this equation, but I have some space above. So I'm going to take these numbers and write them with my equation here. So 25.2 grams of nitrogen. So I've got 25.2 grams of nitrogen and 8.42 grams of hydrogen. And I'm trying to find out how many grams of ammonia can be made. At this level of chemistry, I do not try to trick you. Okay, I try to make problems fairly straightforward. One of the things that students have a hard time with is, what kind of a problem is this? What am I supposed to do? So I'll tell you, when they give you 2 masses in a problem, it's almost always going to be a limiting reactant problem. If they give you 2 masses, that means you're going to have to do 2 calculations and pick the smaller. So that's what we're going to do here. Again, the path is grams to moles to moles to grams. So I'm just going to start with the first one, 8.42 grams of hydrogen. And I want to convert this to what? Moles of hydrogen. Here, the hydrogen is staying the same. The unit is changing. I don't want to change 2 things at once. That's not a good plan. So I want to go moles of hydrogen, and then what do I want to convert that into? Moles of what I'm trying to find, moles of ammonia. And then what's the next term? Grams of ammonia. So there I have it. Grams to moles to moles to grams. If you need to write the path out, do it. And now I'm going to take these units and stick them in here so they cancel out like I want them to. Once you get the hang of this, it is so much easier than trying to memorize a formula. And you can do all kinds of things. Well, the middle term's the easiest. Where do I get the numbers? Balanced chemical equation. So what number should I write in front of moles of NH3? 2. And in front of moles of H2? 3. 3H2, that means 3 moles of H2 will make 2 moles of NH3. Where do I get the number for this term? I need to use the periodic table and the chemical formula. So H2 means 2 times the mass of hydrogen. I'm going to write all the units in here. You don't necessarily have to do that on your paper. 1 mole of hydrogen weighs 2.016 grams. And then over here, I need moles of ammonia to grams of ammonia. That's also a molar mass. Nitrogen and 3 hydrogens. I think it's O3. So then I'm going to put that in here. Be sure to do the math along with me because it's so fun. It's just so fun, right, to catch the teacher making a mistake. I made a couple doozies last night. Everybody makes mistakes. It's okay. So putting this into my calculator, just left to right, top and bottom, 8.42 times 1, divide by this, times this, divide by this, times this, divide by this. I'm coming up with 47.4. Anybody else get that? Okay. Always a good idea to punch it through your calculator twice because it's so easy to make a mistake. I'm rounding it to 3 significant figures because that's what I started with. This one has 4, that one has 4. The middle term is exact. So that's grams of ammonia. I'm not done. This is half of it. I need to do this again using the nitrogen. But now I've got the pattern all laid out, right? So we're going to do another one with 25.2 grams of nitrogen this time. So I'm going to convert this to moles of nitrogen and then to moles of ammonia. Sometimes students go off and they go to some other element. We're trying to end up with the same grams of something. I want grams of ammonia at the end for both of these. The numbers will be different, but the units are going to end up the same at the end. Moles of ammonia. And then I'm going to stick those units in so they're going to cancel out. That doesn't work, does it? Let's fix that. I want grams up here and moles down there. That's better. If you actually go and cancel them and draw that line, then you see, oh, wait a minute, that doesn't work. Moles of N2, so that's going to cancel this guy. Sometimes I work back to front just to mix it up a little bit. All my units in place. 1 in the middle. 1 nitrogen to 2 moles of ammonia. So 2 moles of ammonia and 1 mole of nitrogen. And yes, someone up here in the front noted, hey, we already have this one done. Look, this last term is exactly the same, isn't it? We don't have to calculate that again. So there's a little bonus. And then we need this guy. So we need the molar mass of N2. Write that up here. Always a good idea to actually write this out. So it's good to write all these units in here, but I would say this part right here, that's like the minimum you should write down for calculating a molar mass. Because then you can go back and check your work if your answer isn't coming out right. So 1 mole of nitrogen to 28.02 grams of nitrogen. 25.2 divided by 28.02 times 2 times 17.03. And here I'm getting 30.6 grams of ammonia. I've got 2 answers now. We need 1 answer. Which one do we choose? We're going to choose the smaller. This one might be a little confusing. It says, what's the maximum amount? It's still the smaller of these 2. I can't make 47 grams of ammonia because once I get to 30.6 grams, I run out of nitrogen. And I can't make any more. Even though there's extra hydrogen, I'm done. So just look at these and put a box around the smaller one. So that's our yield. Now, this is not asking which is the limiting reactant, but I'm going to ask you, which one's the limiting reactant? The nitrogen. The reactant that gave us the smaller amount of product is the limiting reactant. Any questions? Here's another one. You want another example? I think so. Let's read the question. The reaction of 185 grams of Fe2O3 with 95.3 grams of CO produces 87.4 grams of Fe. Find the limiting reactant, theoretical yield, and percent yield. This one's a little different, isn't it? Okay, well, let's just figure out what's going on here. I'm trying to get that stupid bar off my computer. What happened? There we go. Okay. So 185 grams of Fe2O3. Well, let's write that here. 185 grams. 95.3 grams of CO. And then it says it produces 87.4 grams of iron. Now it's asking us for 3 things: the limiting reactant, the theoretical yield, the percent yield. What is percent yield? It's the actual yield over the theoretical yield. So we need 2 yields to do that, right? We need the actual and the theoretical. The actual yield is the amount you actually get. When we had the pancake analogy, we said, well, sometimes you burn 1 or 2 or drop one on the floor, something happens, right? How do you figure out how many you actually make? You actually make them. You have to actually do it. This is a problem on a screen, right? We're not doing an experiment. How would we know how much is actually made? They have to tell us. So this number right here, it says this reaction produces this much iron. That's the actual yield. In a problem, they have to give you the actual yield. So we need to identify this is the actual yield. We need also the theoretical yield. How do we find the theoretical yield? We calculate it. That's what we were just learning how to do. So we need to calculate the theoretical yield in grams of iron. We're given masses of both reactants. Two reactants, two masses, that means two equations. So we're going to take grams of Fe2O3 and we're going to find out how many grams of iron could be made. And we're going to take grams of CO and find out how many grams of iron can be made. We're going to pick the smaller of those two numbers, and that's our theoretical yield. The theoretical yield is calculated. Okay, so let's do this. 185 grams of Fe2O3. I want to convert that to moles of Fe2O3. And what's the next unit? Moles of Fe. So this is what we're interested in. And so we're going to take this to that. Grams to moles to moles to grams. So I got to moles, and then I'm going to get to grams of Fe. I know it gets a little tedious sometimes, but you need to write the chemical formulas in there. At least we don't have to write out their full names, right? We don't have to write out iron 3 oxide. Fe2O3 is shorter than that. Sometimes you just have to be thankful for small things. Checking our units, those cancel, those cancel, those cancel. I always like to do the middle term first. 1 mole of Fe2O3 gives us 2 moles of iron. So I'm going to have a 1 down here and a 2 up there. And then I'm looking at this one and this one, and I'm thinking, oh, that one looks easier. I think it's 55.85. This periodic table has numbers that are too small. The mass of iron, the molar mass of iron is 55.85. So 55.85 grams of iron is 1 mole. Now we need the molar mass of Fe2O3. So let's see. Let's squeeze that in up here. So Fe2, that's 2 moles of iron, 55.85, and 3 moles of oxygen. And that's a job for calculator. 159.7. So 1 mole of Fe2O3 weighs 159.7 grams. I'm going to go ahead and calculate this. 185 divided by 159.7 times 2 times 55.85. How many significant figures am I going to include in my answer? 3. I've got 185 here to start with. That has 3 sig figs. That looks like a whole number, right? But it is a measurement. It's not a counting number. It's not exact. So 3 sig figs here, 4 exact, 4. I'm going to end up with 129 grams of iron. Any questions? Now we do the other one. 95.3 grams of carbon monoxide. So we're going to convert this to moles of carbon monoxide. And then we're trying to find the iron still. We're just starting in a different place. So we get the numerator, grams to moles to moles to grams. And then we put units in the denominator to cancel out the things that we want to go away. We want everything but grams of iron to go away. The last term, exactly the same as the one above, 55.85 grams of iron. The term in the middle comes from the balanced chemical equation. 3 COs give us 2 FEs. So 2 Fe, 3 CO. And then here we need the molar mass of carbon monoxide. Let's throw it up here in the corner. It's 1 carbon and 1 oxygen. And so that's 28.01. 28.01. We take 95.3 divided by 28.01 times 2 divided by 3 times 55.85 equals. And this is also going to be 3 sig figs. This comes out to 127 grams of iron. What's my theoretical yield? 127, the smaller one. Call him Theo. So that's one of the things, the theoretical yield. What's the limiting reactant? Carbon monoxide. It's the one that gave us the limiting reactant, LR. Limiting reactant. Percent yield. Well, I'm going to have to erase something to give myself some space up here. We have the theoretical yield. They gave us the actual yield. We're going to put these into the equation. This is going to be the actual 87.4 grams divided by the theoretical 127 grams times 100%. What happens to those units? They cancel out. The unit on a percentage is percent. It's not grams or anything else. So I've got 87.4 divided by 127 times 100. That's also going to have 3 sig figs. And so that's 68.8%. That is our percent yield. Any questions? No questions means everybody got it or everybody's really lost. If you want, well, never mind.